How did the Cold War begin? Well, Western values favored capitalism with the party or parties serving the people, and called it free enterprise. The Eastern Bloc values, the Soviet Union, favored communism with people serving the party, no free enterprise. European values favored a form of socialism, but allowed limited free enterprise with the party or parties ensuring all basic human need. And a number of agreements came into the picture. The United Nations, 1945, North Atlantic Treaty Organization, 1949, something called the Quadripartite, which was mainly for military reasons, 1947. That brought Australia, Canada, Great Britain, the United States all together under that. So we got along very well with the European socialist nations. This made Russia pretty upset because the Eastern Bloc values don't conform with that. Then along comes Nazi Germany, presented a common enemy to all outside political values, led to World War II, bringing them face to face. So who brought on the Cold War? I guess we can blame Hitler. Germany, we're going to get away from all these words in a minute here. Germany and the Nazis' occupied territory became the spoils of war following the defeat of the Third Reich, 1945. And then, can you tell me who wanted to go in and neutralize Russia right away after World War II? Patton, General George Patton. He had a few other people who would like to do it too, but there are reasons why we couldn't. For one thing, we still had a war going on in Japan, and that's where a lot of our war machinery had to go. And it just wouldn't be very politically correct to go in and invade another nation that was your ally for a while. So anyway, what happened was they stole our secrets, and they became a nuclear power also. And so then nuclear weapons, called atomic at the time, presented a standoff barrier to any military resolution of any political differences. So negotiation had to lead to something called détente, or gentleman's agreement, on an international scale. It was an agreement to disagree, more or less. And the agreed dates of the Cold War from 1947 until 1991. We'll talk about that a little bit. Hot wars during the Cold War included, of course, Korea and Vietnam, but these were referred to as police actions. It were not really declared wars, where we were intending to settle civil disobedience between each affected nation. However, it also provided an international showcase of weaponry. Our Phantoms against their MiGs, for instance. The Cold War basically ended in 1991 under both economic and political pressure, mainly via East Germany and the Baltic nations, when the USSR declared no longer to abide by communist rule, which is quite, remember the terms glasnost and perestroika? Those are terms that they came up with saying, we're done with communism, really, kind of interesting. And a quote from the Cold War, Ronald Reagan, Mr. Gorbachev, tear down this wall, 1987. Legacy of the Cold War. The end of the Cold War left the USA and the USSR and other nations holding vast quantities of aging nuclear, chemical, and biological weaponry. Now, although it's a little fear that this weaponry is going to return to its original purpose, there is considerable concern over that of third world rogue or terrorist nations acquiring or building on the resource. We're always concerned about that. Okay, how do you keep the Cold War cold? There are four basic things here. Deterrence, stability through mutually assured destruction, we've all heard that term, MAD, or the arms race, otherwise known as the arms race. Detection, and that's stability through continuous situational awareness, our radars, our tracking mechanisms, keeping track of what your enemy is doing, or your adversary is doing, I should say. Survivability, stability through continuous retaliatory capability. Nuclear hardening, that was my job here. Although I couldn't say we were fighting the Cold War much, but we were meeting the specifications that the government could use to fight the Cold War. That's really what I was told to always say. And then retaliation, the absolute last resort. What's the closest in the Cold War we came to retaliation? Cuban Missile Crisis. That's correct. Okay.
Actually, there was one that was almost
what's that?
worse.
Oh, yeah.
Featuring two Russian diesel-electric submarines with nuclear-tipped torpedoes.
Really? They were? I know conventional weapons were brought to bear for the barricade, but I wasn't aware that they had nuclear weapons.
They were parked off of Florida. during the Cuban crisis
Ah, uh-huh.
and lost communications
there-
with
oh,
Russia.
Is that right? Oh, so that would be bad. That would, because it sounds like Hunt for Red October type stuff. I got to continue. Well, that's a good, interesting point that there was nuclear weapons that were part of that that confrontation. Okay, Cold War. Oops, don't mean to do that. Let me do this right here. Cold War items of interest. Voice of America. We heard a little bit about that earlier here. Radio. I'm sorry. And Radio Free Europe. Radio surveillance, the use of what are referred to as black radios. There's actually a website out there that keeps track of the radios that were used for surveillance during the Cold War. Pine Tree Line, Mid-Canadian Line, Dew Line, North Warning System, and PAVPAWS. These are all forms of radar that were used for that detection portion of keeping the Cold War cold. Civil defense, something we prepared, we're going through here in the United States during the Cold War. Mars, military affiliate radio system, which is kind of on the block right now too. It's being revived. We'll talk about that a little bit later. AT&T Hardened Network, Audiovon, Skynet, the original Skynet. That's before Hollywood got a hold of the term. These are telephone hardening systems. Telephones are pretty much out of the picture now. You have only service providers and the internet, really, these days. Nuclear hardening and survivability, once again. And then Collins innovations during the Cold War. And then Collins had a lot to do with the technology of the Cold War. Now we're going to take a side trip to Hanford, Washington. Has anyone been to any of the National Park Service museums of the Cold War? Could be Los Alamos or Oak Ridge, Tennessee, or the Hanford site. You've been there, Rod? Los Alamos, yeah, for other reasons than the museum, I'm sure, as I recall. They do a lot of different types of research there yet. And then there's a lot of other sites too. Rockwell of Rockwell Collins previously had a site at Rocky Flats in Colorado. Had a lot of bad press on it, but they were the ones who took the plutonium from a site like this and converted it into the parts for nuclear weapons. Incidentally, these are my pictures. I was there just 3 weeks ago, so this is really fresh in my mind. It's a real desolate place, and it's has the Columbia River wrapped right around it. It's very remote, and unfortunately heavily contaminated these days because of the speed with which the Cold War had to unravel. The site that you can visit there is the B Reactor, which is the very first reactor built. It's the world's first full-scale nuclear reactor. It operated from 1944 to 1968, and it produced a great deal of plutonium. In fact, they had a lot of reactors on site at Hanford, all producing plutonium. They did everything right on this one. Very little change had to be made. The engineering was correct from the beginning due to Rico Fermi. We'll talk about that in a minute. This is what it looks like today, the Reactor B site. On the left side are railroad tracks that took the irradiated materials over to the site where the plutonium was reclaimed, and over on, and over on the right side is where you'd enter right there to view the reactor these days. This is a model of the reactor. It has a graphite core. Graphite is a moderator for neutrons. And a lot of shielding around it. The reason this reactor is so well shielded is because operators had to be in there working on it while it was operating and while it was very hot. It has what's called a cold side over here and a hot side on the other side of the reactor. All of the fuel and irradiated material enters from this side and is pushed out the back and down into a water depository where the plutonium is reclaimed. Some of the rods are enriched in U-235, which is what makes the reactor operate, and other rods are enriched in U-238, which is what gets converted into plutonium. These are the control rods here and on the top. They regulate how much power the reactor is going to put out, whether it's in the 100 kilowatt, 200 kilowatt region, what have you. And they had to regulate that to produce plutonium. This is the cold side of the reactor. You can walk right up to it. It's not dangerous here. The back side has a big, thick glass window that you have to look through because that still has contamination back there. It's not bad, and they're very careful to keep the public safe on this. This is a gantry crane across here where the operators would work, and this would go up and down so they could service all these rods, well over 1,000 rods in the reactor. This is the tour guide inside. We had a tour guide on the bus who gave us a tour of the grounds around it. She got lost on the way, incidentally. Funny story. It was because of something they had going on at the time. But we got there. He's pointing right here to what looks like a telephone patch panel, a great big telephone patch panel. It has a jack on it for every one of those rods. Fuel rod and radiation rods I was mentioning before. And he just brought his hand down from pointing across the room. And what he was pointing at is this. These are the monitor panels for every rod in the reactor. They keep track of pressure, temperature, and age of the rods, and how many fuel pellets are inside, and how long they've been irradiated. Caution: bumping panel may cause scram. Those are very sensitive switches monitoring those temperature, pressure parameters on the reactor. And then they let a nuke nerd behind the monitor panel here, and a lot of fun walking back. You can go anywhere you want these days, within reason, there at the site. On the side, there's thousands of little copper tubes. They all go out to the ends of the rod. Incidentally, the water passing through that reactor starts out at the temperature of the Columbia River and ends up at the boiling point in 1 second on the other side of that reactor. And that's probably one of the problems that they had with causing the reactor to scram, was keeping it cool while it was operating. This side measures, I believe, temperature over here. These are all circuit cards that go out to thermocouples in the reactor. These are some, can you see that? Well, I wish somebody put the sun out, will you? These are the tools used to feed the fuel into the reactor. And these are examples of what the fuel pellets and the irradiation pellets look like, irradiating pellets look like right there. So they explained how the reactor was both fueled and the plutonium was reclaimed. This is interesting. These are all the water pipes that feed, we're down in the basement area now, that feed the reactor. And you had to provide proof to the Soviet Union during the SALT talks that you weren't using it anymore. And the best way to do that is to have these all this water feed open with locks. And I imagine the agreement as to how these were kept off these panels. I mean, these cleaning. Actually, they're clean-out ports. How these were kept open and locked so that when the Russians came in, they could inspect it. They said for the first few years they were very serious about this. That's great. For the time after that, they were more interested in coming in, putting a check mark on a piece of paper, and going and buying blue jeans at the local Kmart there. This is what he said. This is Rico Fermi's office right here. He came from, of course, Chicago, where the first reactor was built, very small-scale reactor at Stagg Field, University of Chicago. And this was, oops, I keep doing that. This was his office. And he could, through that window, watch the operation of the reactor and make notes and changes as they were needed. Very, very brilliant in reactor work, of course. This is looking at his office from the backside. These are all the monitor temperature, aging monitors, and what have you that connect to that telephone patch panel I talked about earlier. So they can plug in any rod. They can go out and get the full scoop on it. And one thing I didn't mention before, it's kind of interesting, there's a Frieden Flexowriter there that they could use to print out the information on. The Frieden Corporation did not like their name being associated with the Cold War, with the arms race, so a representative came in one day with a chisel and took the logo right off the front of that printer, and it's still that way today. But anyway, this is Rico Fermi's office. Here's the process of breeding plutonium. Starts out, I could go through this. This is critical mass of uranium and what have you, producing the neutrons. Down here, the neutron goes through a moderator, becomes a slow neutron, gets absorbed by U-238. U-238 becomes U-239, and U-239 is a very short half-life, and it spits off a beta particle, becomes Neptunium-239. That has a longer half-life, but eventually it spits out a beta particle and becomes Plutonium-239. Now these half-lives are very short, like 2 to 3 days for Neptunium. When you get to plutonium, it's over 100,000 years. It's a very stable material, and it's why it was one of the first materials they wanted to produce in large quantities for our nuclear stockpile.
Did they tell you how much they produce?
Yes, they did. It's coming up soon. The next slide, we're going to get there. These are cocooned reactors. These all were the same, same size and operational status as the reactor B. This used to be like a cacophony of activity out here. Water processing stations, railroad tracks, what have you, all bringing the plutonium back for processing. Now this is all very barren, but these are highly contaminated, and they've been cocooned, sealed up completely for I don't know how long of a period of time. There were 9 reactors at Hanford, all working at the same time to produce 70% of all the U.S., actually more than 70% of all the U.S. plutonium bred in the world. You're not going to believe this. A total of 67 metric tons of plutonium was produced during the Cold War in the United States at all of these sites right here. I couldn't believe it. It's online. I came back home and went online to look it up. It's there. We produced over 70,000 nuclear weapons, or nearly, I should say, nearly 70,000 nuclear weapons for everything. They were, of course, delivered by aircraft, the B-1 program, by missiles, by sea, our nuclear submarines. We had spares on top of every one. This wasn't necessarily just for the purposes of reliability, but this was so that we could stand face to face with the Soviet Union, who was doing the same thing, and say we can meet you. Dr. Strangelove, do you remember all the gaps they talked about? We had the nuclear gap. Remember the mineshaft gap? That was the more humorous side of the whole thing. The failsafe is not so humorous. A number of movies were made about the Cold War. But anyway, that's quite a statistic. This is the first plutonium device to be detonated at Trinity Alamogordo, New Mexico, 1945. I think this guy probably got out of there by the time they set it up. And this was the first plutonium. This actually was not plutonium from Hanford. This is plutonium, I believe, that was made in an experimental reactor in Los Alamos. No, I'm sorry, at Oak Ridge, Tennessee. After that, all plutonium, or the vast majority of it, came from Hanford. Okay, Voice of America. We just got this. This was mentioned just a few minutes ago, or in terms of shutting down WWV, I guess. But it was first established in 1942 to promote free enterprise, built up to 42 languages, and the Voice of America came from America. Basically, our policies were very interested in getting nations together and discussing what should be said, that type of thing. Rod, was this the site that you did? This was the Delano, California site.
Yeah, but it wasn't demolished.
Oh, well, no, wait, did you see haven't you seen the pictures of the?
I was there in 2014.
2014? Can anybody get on, and maybe it wasn't the Delano site, but they took down all these antennas very, very delicately with dynamite.
Well,
not at Delano, right? You're saying?
No, that's some other site.
Okay, maybe I was assuming it was because you took the transmitter apart there
Yeah,
at
the
Delano.
buildings and the satellite
Right.
dishes. And
They're still there?
farm and all that was still
Okay,
there. That was-
I will edit this then, that it was taken out of commission, not demolished, okay? I don't know which site was, but there is online there is a Voice of America station, a huge number of antennas, of course, because they.
It might have been Dixon.
Dixon?
There were 2 out in California.
Oh, okay.
Dixon and Delano.
Yeah.
There was another big one in Ohio, definitely Ohio.
That is Voice of America? Because the only ones I knew, the maps I saw earlier were on the coasts, were California and the one at the Edward R. Murrow station at Greenville, North Carolina. But okay, there were 2. There was another one. You're saying? Okay.
Yeah, back in Ohio now is a park with a bunch of soccer fields all around.
Oh, okay.
And a museum.
Okay, yeah, okay. It was okay. Stand corrected. I thought for sure when you said you were dismantling Delano, California, and it just looked just like it. these antennas right here. That's what they knocked. Okay, well, let's not spend any more time. But okay, but like I say, this was their. Oops, this was their logo, Voice of America, and like I say, it originated mostly from America. But remember, I talked earlier about the United States and Europe having an agreement and that led, of course, to Radio Free Europe, or Radio Liberty. It was funded by the United States mainly, but it gave Europe a lot more freedom in providing the news. And there were many stations in Radio Free Europe. I think many more than I didn't research this real well, but then the Voice of America had. But the Voice of America had very high power transmitters, whereas the Radio Free Europe kind of spread out, as I understand, so that they could cover individual nations. They called it Radio Liberty also, government-funded organization. This is right off the net. Information analysis to countries in Eastern Europe, Central Asia, and Middle East, often jammed by the governments of the intended recipients. It still exists today after having gone through many revisions and organizations. Do you remember this? I will bury you. And to the answer is you will not, and one way of ensuring that is tribute to Radio Free Europe. Okay, keeping an ear on them. Now, I just took this off clip art. This is listening to the Soviet military and aircraft spacecraft communications. This is one thing that still remains as somewhat classified. I'm sure anything that they put on the net, online is not going to be classified. This is another thing that got me very interested in post-Cold War era. I own this receiver right here. This came up on eBay. I about fell over when I saw it. The price was pretty good, so I bought it. This is an R1283 ground radio communications VHF surveillance receiver, designed and manufactured by the Airborne Instruments Lab, AIL, at the time where they were a division of Cutler Hammer, back in 1966. And this unit may have seen service in the DEW line or we don't know where. The former owner of it contacted me and he says, "Do you know what you're buying here?" And I said, "Yes, I don't, not all the specifics on it, but I know that it was a surveillance receiver used in the Cold War." And he gave me a little more input on it. They got a lot of view cells to get through. I'd like to talk about each one of these things, but there's some things you look at when you find a surveillance receiver like this. There's no squelch control on it. It's not a communications receiver. It has a carrier-operated relay with lots of outputs for various things, starting and stopping recorders, sending tone messages to SAC, things like that. CW, AM, FM, pulse, it covers all the modulations. It always has a center tuning meter and a relative output meter that has to be able to tune both the video bandwidth and the detected bandwidth. It has a frequency control for CW. Very interesting device, and it uses, let's see, let's go on ahead here. Before I get into that, these are other similar receivers made by the CEI Corporation, LVT I'm not that familiar with, ACL and NEMS. That's of NEMS Clark Corporation. Actually, this probably was the first receiver manufactured at the same time frame as that one I purchased. Then the CEI would have been the second, and then this ALC, which is the Astro Communications Laboratory. They made very high-end devices. They all had to be, these all had to be within a 3.5-inch rack panel. That's because there just wasn't enough room out there in the installations these were put in to have big radios. And they also had to have a pan adapter. None of these radios were classified, but the pan adapters, depending on what it was for, nowadays it's a waterfall display. They've gotten very sophisticated, but the pan adapter was basically a spectrum analyzer. Some of them just gave the spectrum of what you're looking at. Others actually send a program back to the radio to program it for the particular job it's going to do. I think those would be the ones in the classified category. This is Alan Clark and Ralph Grimm. They were pioneers in the development of Cold War telemetry and surveillance receiving equipment, mostly in the VHF and above region. And I'm giving credit to Terry O'Loughlin because I'm stealing from his site there. And that's the thing about earlier when we're going to give credit. Alan Clark actually hired Ralph Grimm. I like these smirks on their face. We got you, Russia. And then later on, Ralph Grimm went on to make quite a name for himself in other surveillance work as well. Now, this device right here, I almost brought one of these in, but it'd be hard to show it around, to pass around and show it. This is called the Induct tuner. This is a Mallory patent. And these were used in most of, actually I've got many, I think, but most of the Cold War surveillance receivers used the Mallory Induct tuner. And I'm going to tell you a little bit why it was really a great device for that use. It was used in that R123 GRC that I showed you earlier that I own, but that had an ovenized environment. It actually was an oven around each of the two Induct tuners that are in there. One tunes from 30 to 90 megahertz, the other one tunes from 90 to 300 megahertz. And all those other receivers did the same thing by government spec. That's kind of the brute force way of doing it. Other receivers used temperature compensation to keep them on frequency. Here's the CE901. That's one of those other receivers I showed you with two Induct tuners here for the low end and there for the high end. Further examples, this let's see, is Watkins Johnson. Watkins Johnson made most of the equipment later on. Very high-tech company, very expensive company. We used Watkins Johnson equipment here at Collins for EMI work and other reasons where we wanted precisely accurate equipment. Okay, this is a linear Induct tuner right here rather than the helical. One thing I didn't point out, I'm going to go back a minute. The way these are tuned is there's a big disc with the frequencies on it, and then there's a little shadow mask or a graticule mask that goes back and forth and only exposes the frequency that you're tuned to at that particular time by the dial. And that's because of this helical design of the Induct tuner. It's in a helix, and so the tuning is also in a helix. And that way it cancels out any variation. Okay, this is a linear version, and I think this is probably Mallory. I couldn't find out who made this, but it would be typical of what they would have patented. Now, the other inductor tuned device of fame is the Collins PTO. Everybody knows what PTO stands for. Permeability tuned oscillator. Actually, engineers these days probably don't, because we've gone to synthesizers now. We don't use PTOs anymore. But it was a tremendous innovation for its time here out of the Rockwell Collins. I'm sorry, not Rockwell Collins, Collins radio fame and history. This is the 70E series used in the 51J and R390 radios and other radios too. This is the inside. I don't want to spend a lot of time here, but I'm really intrigued by how they worked. Rather than a tap on a coil like Mallory used, they ran a core in and out of the tuning inductor right here, the tuning coil. And that's a ferrite core. And it changes the permeability, which will then change the frequency. They're so accurate that they actually use a linear cam, so any minor variations in frequency as you're running the core back and forth, you can actually twist it via this cam and tune out the variation. That's the differential tuning on a PTO. They were precisely accurate and made quite a name for Collins. These are later Collins PTO designs. Rod, you'd be familiar with a lot of the whole S-line series used these, the KWM1, KWM2, this smaller version, the 70K2 PTO. Here's what I own one of these, not the whole thing, just this right here. That's the 70H13, and the A version has an oven in it, so it keeps it on frequency, not only because of being a PTO, being a very stabilized temperature. This was used in the ARC 58 series and a lot of airborne radios. This brought the frequency control into the let me see, I've got it right. Yeah, into the auto-tune world. Auto-tune came about as a way of very rapidly changing the transmit frequency, particularly on radios like the ART-13, which you're all familiar with. I think many of you are. That was a World War II high-power transmitter. You worked the whole HF band, but you had to tune it very rapidly in case you're jammed or you don't want to have the enemy listening to you. But there are lots of coils lots of tuned circuits have to be tuned, and the exciter, grid drive, plate, antenna loading, all that. The auto-tune took care of all that by having automatic stops. And this unit then brought the frequency into the same category because a servo mechanism drove the PTO. You didn't have to be tuned by hand. So you could dial it in, you could use push button control, that type of thing. Benefits of inductor tuning. Linear tuning scale, improved temperature compensation and low environmental effect. Low microphonics. If you take a tuning capacitor, like most radios, the old AM radios and most ham gear, in fact, that didn't have a PTO, if you banged on the tuning capacitor, you could sometimes hear it, particularly if you're at CW. It's because you had all these little plates that would move back and forth, and that's not good if you had vibration. A higher Q factor, we'll talk about that in a little minute, and then low electrostatic effect. If you happen to have a wire passing by the capacitor in there and it's got some signal on it, it'll pick up the E field off that signal, whereas the inductor tuning design used a fixed capacitor, and you'd have to actually change the permeability or introduce a magnetic field in order to get the EMI into it. Okay, this is an example of capacitor tuning. Now, interesting about the capacitor, in, let's say in your old AM radio, is it had a funny shape to it. And the reason for that is because if you tune the capacitor, you have an inverse function, whereas if you tune the inductor, you have a direct function. So at the low frequency end, you had to change the capacitance real fast, and at the high frequency end, you had to change the capacitance real slow. And also, because it's in the denominator, you might say, you had an asymptotic function. That means you're aiming toward dividing by 0, which you can't do. So capacitor tuning requires an inverse function, and is also vulnerable to moisture, dust. Any kind of contamination that gets in here will change the characteristics and lower the Q. I'm not going to spend a lot of time on the math. This is the only math I've got in the presentation. Resonance is, of course, that formula. However, the capacitive reactance changes as 1 over omega C, which is inverse function, whereas inductive reaction changes as omega L, which is a direct function. So you can get linear tuning because as you're changing the inductance, the frequency is changing proportional to it, whereas the capacitor, it's inverse function. So you have to have a funny shaped capacitor in order to tune linearly across the band. And then Q factor over here, I'm not going to spend a lot of time on this, but originally the inductor was the culprit for lowering Q because it had all this wire in it, and that added resistance. When you went to a tuning capacitor, the dielectric, now being air, caused what's called an equivalent series resistance to occur, which actually was higher than the effect that the inductor gave you. So you had a lower Q factor. There's things they did to improve the Q factor in capacitor tune, but you got it kind of automatically in the PTO and in the Induct tuner. Here's an auto tuner. I believe this is out of our ART13, and this would tune the capacitor over here, and there'd be a motor drive on it. You first set the tuning you want, and then you program in a number, and these fingers right here will remember that number, and then you want to go back to that frequency. You hit the servo along with that number, and it stops right where it's supposed to, so you tune the whole radio at once. This allowed frequency, it was an early form of frequency hopping. Yeah, go ahead.
Did you have a Cleveland Institute